In this tutorial I will show you how to model a grid connected PV array in Simulink. Okay, and in this tutorial I will show you a single phase grid connected PV array. Okay, and the model will consist of solar PV array, then boost converter with MPPT controller, then inverter and single phase grid. Okay, so firstly we need a power GUI block. So this is power GUI block, and I want it as it will be discrete, and sample time I want it as TS power, sample time as power, and I'm copying this, and it will be 1e minus 6. Okay, and then we need a PV array. Okay, and its parameter will be 2 in parallel and 9 in series, and module I want it as this one, and it's okay. Click OK, and this PV array will give output maximum about 4 kilowatt. Okay, at 1000 irradiance. So at first I am taking a constant block, and in the later part of this video I will show you in a variable irradiance. Okay, so I'm setting this at 1000, and temperature will be 25. It's okay. Now PV portion is done, and we need series RLC branch because we need DC capacitor here, and I'm choosing this as C, and it will be 1000 E minus 6, and I want to set initial voltage at 260. Okay, now click OK. So PV array and DC capacitor is done, and we need boost converter. Okay, because for converting DC to AC we need 400 volt DC voltage. Okay, so for boost converter then we need AL branch here. This will be AL, and I have calculated its value as 3e minus 3 millihenry. Okay, now click OK. Then for boost converter we need IGBT or MOSFET. I'm taking IGBT here, Control R, and this one. Okay, so in boost converter we need to give gate pulses. For that I'm taking a from block, and we will generate this gate pulse from the MPPT. Okay, and I'm renaming is as PWM as B. Okay, then as a boost converter part we need diode. Okay, and then DC capacitor here again, because we need to convert this DC to AC, and we will use inverter here. So this capacitance value will be 3000 E minus 6, and initial capacitor voltage as 425. Okay, now this portion is done, and we need to measure this DC voltage. So and I'm taking a go-to block, so this is VDC. Okay, and tag visibility it will be global. Now we have our DC voltage. Now we need to convert this to AC because we are dealing with a grid connected PV array. Okay, here for inverter part I'm taking universal bridge. Okay, and we have to rotate this. So format, flip block, and left right. Okay, and we are dealing with a single phase. In the next video I'll show you three phase. So this is bridge arms will be 2, and power electronic device I need to use IGBT diode. Click OK, and this is our inverter. Okay, now similarly we have to give gate pulses here. So this will generate from inverter control, and we will make the whole inverter control here. So here this is gate, and we will generate the gate signal. Okay, so here we have our PV array, boost converter, and inverter, and here we need LC filter. Okay, so here basically I will use LCL filter here. So this will be R, and resistance value will be 8.2 E minus 3, and inductance will be 2.18 E minus 3. Okay, so here this is L, and similarly we need series RLC load, and here before adding this I need to add AC voltage source. It will act as a gate. Okay, so our peak amplitude will be 240 square root 2. So this is for 240 volt RMS. Okay, and frequency 60 Hz is okay, and this is series RLC load, and our nominal voltage will be 240, frequency 60 Hz is okay, and active power it will be 10, and I do not need any reactive power, and capacitive power we need at 520. Okay, now click OK. So this is our LCL filter. Okay, and I have divided this by 2 because adding the RL branch in both side give more good value. Okay, so this is our LCL filter, and this is our grid. Okay, so this is our grid. Now we need MPPT controller to get the gate pulses. Okay, and here I have already made this MPPT controller, and I'm copying this MPPT controller and I will paste it here. Okay, so this MPPT controller take input voltage and current from PV array. Okay, so we need a GoTo block, and this will be yes PV measurement of PV. Okay, so it's okay, and okay, so from it will be yes PV, and click OK, and we need bus selector block because we need voltage and current here. This is voltage and this is current. Okay, click OK. So this is voltage and this is current. Okay, and inside MPPT controller, this is mainly P part of an observe technique, and you can take a snap here or you can write this. I'm showing the whole MPPT function here. So this is the MPPT control function. Okay, so I'm scrolling this, and this is the whole one. So okay, you can write this inside your MATLAB function. This is the MPPT function I used in this model. Okay, so here we need add block, because this MPPT controller will give us the reference voltage. Okay, So to get the pulses or boost converter pulses, we need to convert this to PWM or get signal. So this will be minus plus and connected here, and B will be connected here, and then we need a PID controller, and controller type will be P, discrete type, and sample time will be TS power. Okay, and proportional will be 0074, and this value gives a better output. You can also optimize it, but it will work in this model. Okay, click OK, and now we need a PWM generator, DC. Okay, so this switching frequency I want it as 10E3, and sample time will be TS power. Okay, now click OK, and then this PWM will generate the get pulses for the boost converter. Okay, so now go to tab, and it will be this one for the boost converter. Okay, now Control C and Control V. Okay, so now so far we have our PV array boost converter operating with the MPPT controller using power and observe technique, and we have our inverter and our NCL filter with grid. Okay, so now we need to generate the gate pulses for the inverter control. Okay, so before grid we need some measurement block here. I'm taking current measurement block, and voltage measurement block is present here. Okay, so this will give the voltage, and this will give us the current. Okay, okay, so similarly I'm taking go-to block. This is gate current. Okay, so let's renaming it as iGrid. It will be global. Similarly this will be our vgrid. Okay, now everything is okay. Now we have to generate the control logic or get signal. Okay, so for that it will take some time, because we are dealing with single phase. We need to convert the single phase signal to DQ and some conversion. So for that I'm taking a subsystem block here. Okay, so in the subsystem block we will generate the gate signal for this inverter portion. Okay, now inside this subsystem we have to convert our grid voltage and grid current in DQ frame. Okay, so firstly I'm dealing with grid voltage, and I'm taking from block here, and we need a vgrid. Okay, so in this whole control process I want to deal with the in per unit quantity. Okay, so for that we need to convert this grid voltage into per unit quantity, and it will be 1 divided by, sorry, it will be 240 SQRT2. Okay, so this will ensure the grid voltage in per unit quantity. Okay, so then we need a PLL block, PLL single phase, and inside PLL initial input frequency 60 Hz is okay, because we are dealing with 60 Hz, and it will be TS control. Okay, sample time I want it as TS control, and I will copy this and Control V, and it will be 1e minus 5. Okay, now go to this omega t, because omega t will be useful later part, make it global, and this portion is a frequency f. Okay, so it's okay. So now we have our grid voltage in per unit quantity. Now we have to convert this to uh, VD and VQ form. Okay, so and here I will take fundamental PLL driven block, and here frequency is the output of the PLL, and omega t is similarly here, and input will be the grid voltage. Okay, so this angle will give in degree. Okay, so now we have to convert this to radian, so this will be pi divided by 180. Okay, so now we need magnitude angle to complex form. So this one is magnitude and this one is angle. Okay, so this complex form, and again we need a real and imaginary part. Okay, because we need a VD and VQ, so we need complex to real imaginary. So this one is complex, and this will give us the real part, and this will give us the imaginary part. And here we need a max, and this will give us the VD and VQ. Okay, so this is VD and VQ, and tag visibility make it global. So okay, so now we have converted our grid voltage into D and Q format. Okay, now we have to convert our current or grid current into D and Q frame. Okay, for grid current I'm taking from block here, and it will be our grid current I grid. Okay, okay, and similarly we have to convert this grid current into per unit quantity, because we are dealing with per unit system. Okay, and it will be 244,000 and square root and 2. Okay, so this value will confirm grid current into per unit quantity. Now I'm taking a subsystem block. Okay, because I need clean format here. Okay, and this is our subsystem, and this will be this one is input, and the frequency will be used here. So this will be frequency, and this omega t. Okay, this will be omega t, and the three are number one is input. Okay, now here in this case I will use alpha beta to DQ format. Okay, so okay, for that I'm taking the frequency block here, and I'm taking a saturation block to limit the current saturation like 70 and 40. Okay, now for to get the alpha beta form, uh, I need a math function, and it will be a reciprocal. Okay, and gain because we need to delete a 1/4 cycle 1/4 for the beta signal. Okay, and gain will be 1/4, and everything is okay. Now I need a discrete variable time delay. Okay, and the input will be this one. Okay, this is our input, and this delayed portion will be inside this one, and sample time will be TS control. Okay, and then we need max, and max input will be 3. Okay, so here you can clearly understand this, the number 3 is our input, so this is our alpha signal, this is the delayed portion, this is beta signal and alpha beta 0, so we need constant block as 0. Okay, so this value will be 0, so this is our alpha beta 0. Okay, so now we need alpha beta 0 to dq, so this is our alpha beta 0 and this omega t will be used here, and here in dq0 we need just d and q. Okay, so I'm taking a selector block and the selector block index will be 1 and 2. Now click OK, and I'm taking a goto block and it will be our get current int id and iq format. Okay, so this is get current in id iq and tag visibility will be global, and I'm also taking out block. Okay, so this will be id iq. No, it's okay. So we have our gate voltage in the dq format and similarly our gate current in dq format. Okay, now I will generate the reference current from the dc link voltage, from the this dc voltage. Okay, so inside subsystem, for reporting getting the reference d current, firstly we need dc voltage, and this dc voltage will come from this one vdc. Okay, so inside this one, and it will be vdc. Okay, and I want to take a mean block here. Okay, and fixed here is okay, and sample time I want it as ts control, it's okay, and initial it will be 425. It's okay, and this will be our mean dc voltage or vdc mean. Okay, and make it global, click OK. So this is our mean dc voltage, and from this one I will generate the reference current. Okay, so I want the constant dc voltage as 400. Okay, and this from, and this the vdc mean voltage will be used here, so this will be vdc mean, and we have to subtract this, and this sign will be minus and plus. So from the vdc mean we will subtract this constant dc voltage we want, and then as we are dealing with per unit quantity, so we have to divide this by 4400. So, and then we need a PID controller. Okay, and it will be P and I, and discrete time and um, proportional and integral value will be 12 and 200. Okay, and discrete time, and it will be TS control. This is TS control, and I want it as to limit the output as upper limit as 1.5 and lower limit as minus 1.5. Okay, so this will give us the reference current, which is called id ref. Okay, so make it global, and we need id and iq. Okay, so for that I'm taking constant block again here, and its value will be 0, and marks it here. So this is our id reference, sorry, so this is our id reference, and this is our iq reference. Okay, So this is our IDIQ reference. Okay, so we have our gate voltage in DQ form and gate current in DQ form and reference current in DQ form. Okay, so now we have to regulator current. Okay, and I'm taking another subsystem block for the current control. Okay, so this will for current regulator, and I'm deleting these browns, and here this IDIQ will be used here. So this is IDIQ, and this IDIQ reference current we need. So this will be IDIQ reference. Okay, connect it here. So this is IDIQ reference, and this VDVQ lastly. Okay, so from this control V VDVQ. Okay, and connect it here. Okay, so at this stage we have our gate voltage in the DQ form, and gate current in DQ form, and IDIQ reference current. Okay, so from this we will generate the gate voltage in VDVQ in modified form. Okay, and here I will use the feed forward control. You can do internet or ChatGPT or anything like this to know about the feed forward control. Okay, so basically I will implement the feed forward control here. So for this we have our IDIQ, and we need to feed this to uh, some block, this minus and plus. So this is our IDIQ, and this is our IDIQ reference. Okay, so from this we need a PID controller block here, and it will be P and T type, P and I type, and sample type will be TS control. TS control, and proportional will be 0.15, and integral will be 6.6. Okay, and I want to also limit the output as 1.5 and minus 1.5. Okay, now click OK. Sorry, it will be minus 1.5. Okay, now this is basically the equation of feed forward control. Okay, and here I'm using a Dmax for the IDIQ reference. Similarly the VDVQ format. Okay, and we need two different block, and first block will be plus plus minus, and second one will be plus plus and plus. Okay, so this will be for VD, and this will be for VQ, and here uh, from IDIQ reference we need two gain block. First one will be, this is basically come from the filter portion. Okay, 0.002, and it will be ID, and for IQ it will be 0.2. Okay, so similarly for 0.2 it will be from ID. Okay, and for IQ it will be 0.002. Okay, now we have to max this ID and IQ because this is in the form of id and iq. So this is id and this is iq. Now we have to add this one, and here I want to use a saturation block here to 1.5 to -1.5. Okay, and go to block which keeps the VQ in converted form. Okay, make this global, and from this VQ converted we will generate the get pulses. Okay, so take the out block here, and similarly Ctrl C and to B. Okay, so everything is okay. Now we have our VDVQ in converted form. Now from this one we generate the get pulses for our this inverter portion. Okay, so for that I'm taking also another subsystem block, and which will give us the reference signal, and from this reference signal we'll generate the get pulses. So let name it as reference signal generator. Okay, and inside reference signal it delete this, and here VDVQ converted will be used here, and we will use this VDC min to generate the reference signal. So I'm taking this one as from, and it will be V and VDC min. Okay, and this omega t will be used here. So from this will be omega t and omega t. Okay, so in a reference signal generator we have VDC min, so I'll be used here, and we have to compare this VDC min to our peak AC voltage. Okay, so it will be 240 square root 2. This is the peak value. Okay, so this is our VDC min, and we have to divide this one VDC min and square root 2, then VDVQ converted will be used here, and this will be divided by this one. Okay, now we have to demax this because we have in D and Q format. So let demax this. Sorry. Okay, so this is in real and imaginary part, so we have to convert this to angle magnitude. So I am converting this real imaginary to complex. So this first one is real part and second one is imaginary part. So then we have to convert this complex to angle magnitude. So this is angle, and I'm taking a product block. This is the M value for a reference signal. Okay, so I'm connecting this one, and at this stage we have to this angle will be our reference signal angle, and our reference signal will be sine. Okay, and before adding this I want to also compensate for our control part. Okay, so we have to add this another part, and this omega t will be used here, this omega t, and I want constant, and this constant value will be 2 by our frequency was 60 Hz and our TS control value here. Okay, so TS control. So this is our reference signal or U reference. Okay, so this is our U reference. Okay, so everything is done. We have generated our reference signal here. Okay, so this subsystem is giving us the U reference value here. From this U reference, we need a PWM generator to get the get pulses, and it will be 2 level. And this is our U reference, and it will be for single phase full bridge, and frequency I want it as 5E3. Okay, and sample time it will be test power, and everything is okay, I think. So delete this gate and connect this gate to here. Okay, okay, so everything is done. I think now we have to add scope here, and we want to observe this grid voltage and grid current. This will be V grid and I grid here. So this is grid voltage or V grid, and this is our I grid. Okay, now stop time 1.5 or 2 is enough. I'm taking 1.5. Don't worry, I will also use the variable irradiance. First I'm checking this model whether it's working or not. Okay, so let's run this model. Okay, we have some problem here. We have to click OK here. Okay, now it's working. Okay, now let's check the output. Now you can see it's working quite well. Okay, and now you can see our current level is above 20 here. Now let's change the irradiance value to check whether the controlling part is working or not. I am changing it to 500. Now the current should decrease here. Okay, now click hit enter. Now you can see here our gate current to is decrease a lower value, and it will take some time uh, at transient condition. And now you can see here our current is decreased to about 10 when our irradiance value is 500, and then I again change the value to 1000 again. The current should increase. Okay, now you can see here now you can see the current is increased here in about 20. Okay, now we can confirm that our model is running. Okay, now I'm stopping this one. Now I'll check the THD here. Okay, total harmonic distortion, and I want to observe the THD in grid current, and I'm adding a scope in grid current, and let's make a setup here. Like in logging we have to log the right workspace, and it will be structured with time. Now click OK. So it's okay. We have to set some modeling parameter. After working with THD, I will change this to variable irradiance. So in data import export, all will be all checked, and this 3 will be checked here. Now click OK. This is for total harmonic distortion or THD calculation or in per V block. Okay, so we have to run this model again, and I'm adding stop time as 0.4 second is enough. I think it's okay. Now run this model again. It will take some time because my laptop is not so strong. Okay, I'm not skipping this video here, and it's working, huh? Okay, the simulation is done, and this is our grid current. Okay, up to 0.4 second, and we have to go in Power GUI and apps and FFT analyzer to observe the total harmonic distortion THD in our grid current. Okay, and it will take some time. Just hold on. Yes, it's working. So this is our grid current and signal like it's okay, and first up to 0.06 or 0.07 it skips some transient. Okay, so I'm taking start time as 0.2 is good or enough thing. So a start time is zero point 0.2 and number of cycle 1 and fundamental frequency 60 Hz is okay. Now complete FFT. Now you can see our THD is about 1.37%, which is very much less than about 5% THD. Okay, so this model is valid and you can use this model. Okay, so this is all about this video, and now I will add a state generator block to model this in uh, variable irradiance. Okay, okay, and I want it as point 2 and it will be 0.4 and 0.6. Okay, and amplitude I want it as 1000, then 800, then 600, and then 500. Okay, and the current should gives output in a decreasing format. Now we have set 0.6, so zero point 0.7 is enough. Now I'll run this model and I'll show the output here. So at this stage I am pausing this video here, and when the output is ready I will show you the output. Okay, so our simulation is done. Now here we get an iGrid. Now you can observe the current nature here. So up to 0.2 second the current is about 20, so zero point 2 to 4 the current is decreased a lower value, then zero point 0.4 to 0.6 this gives more lower value, and then 0.6 to up to this gives more lower current. So our current controlling is done here in this model, and our total harmonic distortion is less than 1.5%, which is very good. So this is all for today. In the next video I'll show you in single phase, but I will not use the boost converter here, and it will be a single stage grid connected PV array. And in the next video I'll cover the three-phase grid connected and grid to vehicle or vehicle to grid and so on. And if any information you need I'll put this in the video description, you can check this. And so that's all for today. Thanks for watching.